Hi, this is Ray Roque, and this is my solution to the ENPM701 Autonomous Robotics Course Grand Challenge of the Spring 2026 term. This year, the Grand Challenge was inspired by the recent innovations in autonomous agricultural technology, especially companies like Burrow and Jarbo that have been leading the charge to create self-operating farming equipment. This equipment can do tasks such as planting, monitoring, and harvesting crops. Along a longer list of things that they can do. As such, my robot this semester is meant to recreate the harvest, transfer, and bin task these robots would normally do. The challenge took place in a 10 by 10 testing area with a predefined launch location as seen on the bottom left corner of the graphic. As and it also had a predefined collection area, which is in the top leftmost corner. It also had 4 available QR codes to help with localization using the camera to help complement the IMU and encoder readings, as well as the distance sensor. The goal of the robot was to autonomously navigate in a cluttered environment in this box in order to find and deliver 9 blocks of various colors to the collection area. The block locations were randomized before the start of each run, and the robot had to return them to the collection area in a specified color order. This took a combination of computer vision, localization, controls, and planning techniques to accomplish. Somewhere along the process of building my robot, I started to affectionately refer to it as RoboPie, so I will be referring to it as such going forwards. Here is the breakdown of the main hardware components and software packages that made RoboPie possible. The brains of the operations is a Raspberry Pi 4, hence the name RoboPi. This robot sensor suite is composed of an encoder for reading motor rotations, an ultrasonic sensor for measuring distances to the walls, an IMU for heading readings, as well as a camera for block recognition and location estimation. The wheels of the robots are controlled by 4 motors, and the robot has a servo motor gripper that is used to grab the blocks. These motors are powered and controlled with the help of an H-bridge. Most of the software stack for the software stack, I chose to abandon the supported Raspberry Pi operating system, as I found although it was very efficient on the Raspberry Pi, I preferred the support I would get using Ubuntu, as this allowed me to use Rust 2 as my robotics framework, as well as Python and OpenCV for my programming and computer vision needs. This was a very powerful tool for helping me achieve highly dynamic and complex behaviors. Here are just a few images of building the robot. What I had in the table there is the very first day of building. It's just all of the components of the DF robot Baron kit. Actually, building out the kit was relatively straightforward, but it was pretty challenging sometimes with the low tolerances in some of the components. This was especially notable when mounting the motors, as adding the encoders to the motors, the encoders themselves would hit the motor and they would grind. So this would cause improper encoder readings as well as mess with the motor's functionality. So this is after mounting the motors and the encoders. The encoders are used to control forwards and backwards movement as well as to estimate the travel distance. So this test was just moving the wheels specified distance forwards and then backwards. So after getting the motors and encoders working, I added in the gripper, the servo gripper, as well as the ultrasonic sensor. The ultrasonic sensor was mounted temporarily in a mini breadboard. However, I quickly realized that was gonna be an issue because I was still missing space for my IMU as well as another component. So I quickly shied away from that and chose another solution. So I ended up opting to use micro breadboards for the distance sensor and the IMU, as well as the Arduino Nano. This allowed me to fine-tune the locations of the sensors more easily, as well as in the future, if I want to hide the cable wiring, now I have easy access to all of the apertures in the chassis to run the cabling through. Here's what RoboPi ended up looking like in all its glory. The cables are a bit of a mess, however the components are assembled in a way that allows for hidden cable routing. I kept them exposed and longer than needed for easier debugging, but in theory now that I have proven the robot works, I should be able to just trim those down to make everything look neater. I use HSV masking as well as edge detection to detect the blocks. The center of the detected block was then used to estimate the block's position relative to the robot. Once a block was detected, the robot will send an angular position command to a controller to point the robot at the block. This was done using a closed loop PD controller alongside the IMU. The same process was used alongside a path planner using A-star to navigate towards a block and pick it up. My best friend for this project ended up being Visual Studio Code, as it allowed me to remote into my Raspberry Pi while keeping the root folder accessible and working on a working ID functionality. I could edit my files from my computer without having to make the Raspberry Pi run my editor and a GUI. So this allowed me to run a headless. Then all I had to do to start my robot was send a single rust to launch command in the terminal from VS Code uh, to the Raspberry Pi, and then everything would be run locally on the Pi. That out of the way, this is RoboPi attempting the challenge with a total of 9 out of 9 blocks successfully delivered. Quick shout out to Chanel laying on the couch as RoboPi was really giving it its all. This will not have been a successful semester for me without the doggy supervisor around. This course really allowed me to integrate most of the areas I have learned during my studies, so I would recommend it to anyone looking to round off their uh, professional robotics masters. Now that the course is over, I will get to experiment with this robot, which is great. I have some plans already of upgrading it to a Raspberry 5 I have laying around, as well as adding a depth camera and a LiDAR. I want to see, and I also have to find something else to do other than the Grand Challenge, so find a useful task for it, because I want to test out like more advanced localization techniques as well as SLAM. Maybe I will post an update on that once I am done. But for now, this has been my ENPM701 Grand Challenge submission. So thank you very much for your time.